Good morning. Let's start lecture. Okay, so the next topic we're going to talk about is optimal control. Okay, and so this lecture will serve as a sort of review on some of the basic concepts before we dive into this linear quadratic controller. Okay, so LQR. So the concept basically is about the mean and max and Lagrange multiplier. Or in other words, we're going to look at or to take a quick review is constrained and unconstrained optimization problem. Okay. So some of those material actually covered in 248, but just to serve as a quick review here. Okay. So let's say the first one here. I'll say unconstrained. Okay. So unconstrained problem. Start from the very simple one. If you have a function of a single variable and you're looking for the minimum or the maximum of this single variable, right? And then what we know is we're going to take a first derivative and then take a second derivative, right? But the idea is always it's always kind of come from a Taylor series expansion. So if I take a Taylor series expansion of this function at the x equal to a, right? So basically, let's see if I take Taylor expansion at x equal to a, then it's f of x equal to f of a plus the derivative f at x equal to a, then x minus a, then plus f double prime over 2 x minus a squared, and then plus the rest of the higher order terms, right? Yeah, that's Taylor series expansion. So apparently you look at this way here, so then if you move this f of a to the other side, okay, so let's call it delta f. So this is basically f prime of a x minus a plus high order. Okay, so if I get rid of this high order here, then this is basically the approximate sign here, right? Okay. Now, for finding the mean or max, right? Finding mean or max meaning at the mean or max location, your first order derivative will be 0, right? And when this guy is 0, then the delta f will basically depend on this high order, the second order derivative. Okay. So delta f is approximately this guy. So this is basically pretty clear now. So what makes this x equal to a is a mean, local mean, or local max, right? And it depends on basically the sign of this second order derivative added here. Huh? Yeah. So if this guy is greater than 0, right? If this is greater than 0, meaning a little disturbance, okay, from x equal to a. Oops, I forgot to. So a little disturbance from x equal to a, which is the delta f, is always what? Is always greater than 0, right? So if this is greater than 0, then a little disturbance, and this is always greater than 0. So here is x equal to a. A little disturbance from that is always greater than 0. So basically, if this is equal to a, then a disturbance from x equal to a. Sorry, let me draw it wrong here. A disturbance from x equal to a. So you use any values beside the x equal to a there, then minus this value is greater than 0, right? So which means what? then x equal to a is a local mean, right? So that's basically the idea. And the second one here, if this one is less than 0, then that means this is a local max. Okay? Yeah. And there's another extreme case if this is guy 0. If this guy is 0, that means actually this approximation sign is delta f is become what? 0, right? Yeah. So you can't tell anything. So if you want to know what happens, you actually would have to look even a higher order, right? A third derivative. So basically, when this is 0, it's inconclusive. Okay, so you can't make a conclusion if this is 0. Okay, yeah. So that's the single variable, right? This is a single variable for unconstrained here. And then we can take a look at the second one here. There's a multivariable at here, and we'll make use of this as a typical example for our next Lagrange multiplier. So let's see if I have a multivariable, okay, function of two variables, okay, function two variables here, and I'm trying to find, right? Let's see, the objective is to find, okay, the local mean or max, okay, of this function. Okay, yeah, the extreme value of this function here. So, function of two variable basically means what you have is a surface. Okay, yeah, it's a surface. Then you change basically your x, okay, in the xy plane, and then you look for, okay, the corresponding value on the surface, and then you're trying to find whether that point is a local mean or local max, right? That's the idea here. Okay, yeah. So as we learned actually, in the 248, so what we do is basically we use that idea is same as this one here. You have a first derivative test, you have a second derivative test, right? Yeah. So, but in this case, the first derivative test is not just f derivative now, it's basically the gradient, right? Yeah. So gradient is a vector. Okay. In this course, we will always use a column vector here. Okay. So gradient is a vector. It's a partial derivative f over x, partial derivative f over y. It's a vector pointing to the direction of the greatest increase of this function z. Okay. So if it's a direction, basically the gradient delta f. Okay. Let's say in this case, okay, because it's function two variable, so the gradient vector is in the xy plane. So it's pointing to a certain direction, and that direction is the greatest increase, representing the direction greatest increase for the function. So if you go along that direction, then you're supposed to, that point on the surface supposed to go up, right? Yeah. So apparently, if this point, right, is at a local mean, a local max location, then at the location, there is no direction for you to go anymore, right? So then that means this guy, right, is 0. Okay, so this is basically first derivative test. Okay, so you set this gradient vector to 0, then you solve this equation. Then the solution based on this equation is what we call the stationary point, right? Yeah, so solution in here, and they are stationary point. So stationary point means local mean or local max could happen at this stationary point, but not necessarily the stationary point will give you a local mean or local max. And there are situations, for example, if you recall that there is a so-called what? Saddle points, right? So remember what a saddle point is? So yeah, like a horse saddle, right? So you go one direction, you go down, right? You go the other direction, it goes up. So it's hard to say whether it's a local mean or local max. Okay, yeah. But first derivative test, the stationary point will give us contains the local mean or local max, basically. Okay. So the question is, okay, so how do we decide on whether this stationary point is the local mean or local max? So then we do basically a second, right? A second derivative test. Okay, second derivative test. So second derivative test, there is this theories, right, regarding the second derivative test. But I'll give you just like the first one, the Taylor series. I'll give you a sort of a not a rigorous proof here as to how the second derivative test or theorem is derived. Okay, so second derivative test or theorem. So here's the idea here. Okay, if I'm gonna expand, okay, so I'm gonna expand this function, okay, at x0, y0. Okay, so take a Taylor series expansion of this function at x0, y0. So then what do we get? So this is a Taylor series expansion for multivariable function. Okay, yeah. So it's approximately equal to, okay, f of x0 plus y0 plus partial derivative f of x, okay, x0, y0, x minus x0, plus, okay, fy, x0, y0, y minus y0. Okay, so that's the first order, okay, partial derivative. Okay, and then we'll go to the second order only. So for the second order here, and this guy end up with, you know, I'm gonna rewrite this just a little bit here for this term at here. Okay, for this term here, I'm gonna just rewrite it just a little bit here, write it into a matrix format. Okay, so I'll save myself a little bit writing it here. Okay, that's the first. That's that term there, it's the matrix. Okay. Second one here is also, you can also put that in the matrix, and this is going to be this format. Okay, this is row vector, and then times a matrix at here. So fxx, fxy, fyx, fyy. At, let's see, this is a p naught. Okay, so plugging the p naught coordinates, then x minus x0, y minus y0. So, and then plus the high order term. Okay, so if it's a approximate sign there, so I can just get rid of that. That's fine. Okay, so that's Taylor series expansion for a function of two variables. Is that good? Yeah. So if I'm gonna do this here, let's say define a vector p as this x and y. So this is the current x, y. If I define a p naught, you know, which is the vector or the coordinates of the current one there. Okay. Yeah. Now if I look at this one here, this one, this is basically what? This vector, that's basically the gradient vector, right? It's basically gradient vector here. So then f of x, y, okay, so f of x, y, right? I can write it as f of a p. So this is basically a function of this x, y here. And that's approximately, this guy here is f of p naught, right? P naught. And this one here, this is a gradient vector, but my gradient vector is defined as a column vector here, right? Yeah. So this is essentially the transpose of the gradient vector, right? Yeah. And this is a gradient vector at the P0 location. Okay? Yeah. Then times this. And what's this? This is basically P minus P0, right? And the second term here is 1/2. First one, this is what? P1, P minus P0 transpose, right? And this matrix here, this is a second order here, right? It's second order. So this matrix is actually called the Hertzing matrix, or this matrix is, I'm not sure if you learned this, it's basically the Jacobian of this vector here. Okay, this vector. So let's call this is H. Okay, so this guy here, let's call it H here. So H P0. Okay, and then P minus P0. Okay, so our multivariable function, right? Expansion of the multivariable function, Taylor series expansion, can be simplified into the writing like this. That make sense? Yeah. Now, this actually doesn't restrict to just a function 2 variables. You know, think about that. If you have a function of 3 variable, 4 variable, 5, or any number of variables, all you need to do is just what? Just expand this vector here, right? And this Hertzing matrix, this matrix, instead of 2 by 2, depends on the number of variables. Then you would have, if it's n variable, then you have n by n at here, right? Yeah. So now let's get back to this find the local mean and the local max case. So local mean, local max means we do a first derivative. So at the local mean or local max or the stationary point, this term is 0, right? So this term is 0. So ultimately, what we have here is, if I move this term to the other side, we basically get delta f, right? The change delta f is approximately equal to the second term. Okay? Yeah. So 1/2 okay, at stationary point. Okay? Yeah. So the second term at here is called a quadratic form. Okay, so this is basically a quadratic. Actually, the whole thing, this whole thing here is a quadratic form. Okay. Okay. Yeah. So why is it quadratic? It's basically, this is this is like this, right? X 1/2 ax squared. Okay, if it's just a scalar. Okay. 1/2 ax squared, that's quadratic. Now because this is vector, so it's not exactly like this, but it's basically like this. Okay? Yeah, that's called quadratic form. So then, and just like this, a function of single variables. So what we need to decide is, we need to decide whether delta f is greater than 0, less than 0, right? So we can determine whether we are at the local mean or local max, right? Yeah. So this Hertzing at here, this Hertzing matrix, is essentially like this second derivative, this guy here. Okay, right? So, but second derivative is scalar quantity. You know, I can check whether it's greater than 0 or less than 0, right? So I can look at the value of that. But this is a matrix. Right? This is a matrix at here. But this whole quantity is a scalar. So what makes this quantity to be greater than 0 or less than 0? And that's actually basically the idea, so-called positive definiteness of the matrix. So basically, this guy here, okay, so this guy here, let's see if I call this is a delta F here, right? Yeah. So 1/2 P minus P naught transpose H P naught P minus P naught. So this term will be greater than 0 if this matrix P, okay, is positive, okay, definite. Okay, it's positive definite. Okay, so this is a pretty useful idea, you know, in terms of the matrix linear algebra. It's a positive definite. Okay, yeah. Or in other words, if this is less than 0, then it's a negative definite. Okay. If it's a greater equal to 0, it's called positive semi-definite. Okay. Yeah. But anyway, so we'll focus on this positive definite here. Okay. So if your second look here is this matrix H. This matrix H headed here is actually what? A symmetric matrix. Okay? Yeah. As long as you have a continuous function, if the second derivative is continuous, then fx is equal to fyx. Okay? You know, there are situations not continuous, these two are not the same. But anyway, if we deal with a nice function, then this is a symmetric matrix. Okay? Yeah. So we're dealing with function of two variables. So what makes, let's say if I have a matrix, okay, if I have a matrix of 2 by 2, let's say this is a matrix A, so A, B, C, D, for example. Okay, yeah. So let's say maybe we should write it this way here. Let's say matrix here. Let's say this is a symmetric matrix, right? So let's say this is B, B, C. Okay, A, B, B, C here, symmetric. Okay. So for a 2 by 2 matrix like this, how do we determine whether this matrix is a positive definite matrix or not, right? So there are different ways of looking at it. One way looking at the positive definiteness of a matrix is this. You take the determinant, okay, of each one of the sub-matrix. So for example, look at this one, whether this is greater than 0 or not. Then you look at this one, okay? And if you have a 3 by 3, then you look at this another one. Okay? So it keeps going, right? Yeah. If the determinant of all of the sub-matrix are all greater than 0, then it is a positive definite matrix. Okay? That's one way of looking at it. And the other way of looking at it is basically you can also look at the eigenvalue of the system here, right? So this guy is PD. I'll call it PD at here. Okay, positive definite. Okay, this guy is PD if eigenvalue lambda 1 is greater than 0 and lambda 2 is greater than 0. Okay, that's one way of looking at. The other way of looking at it, as I said, is a determinant, right? It's basically determinant. Okay, test is A has to be greater than 0, and this 2 by 2 determinant needs to be greater than 0. So this is AC minus B squared greater than 0. Okay, yeah. So those are ways of looking at it. Okay, so I'm gonna make use of this guy here. Okay, let's make use this here. AC minus B squared greater than 0, and also A has to be greater than 0. Give us a positive definite. So then, what's H? This is H here, right? This is H. Then the condition make it a PD is fx greater than 0, and then determinant is greater than 0. Then if these two conditions satisfied, guess what kind of a location we're looking at, local mean or local max? Positive definite. So positive definite here is equivalent to this case, right? This is the case here. Okay, so basically, with a positive definite, then this whole term is greater than 0. So delta f is greater than 0. Okay? Yeah. So that's basically the second derivative test or second derivative theorem. So the theorem basically says, right, x naught y naught, right, is local mean if, okay, fxx is greater than 0, and also the determinant is greater than 0, okay, at this location. Okay, yeah. That makes sense? And then this guy will be local max, okay, if this matrix is not positive definite. So what makes it not a positive definite is, so when the a is less than 0, okay, when a is less than 0, then this guy is still greater than 0. Then it's a positive, it's a negative definite matrix now. Okay, yeah. So basically, when fx is less than 0, and at the same time this term is still greater than 0. Okay, yeah. And the third condition is that x naught y naught, okay, is a saddle point. Okay, it's a saddle point, and that's when the determinant for this guy is less than 0. Okay, that's when this guy is less than 0. And the last one here is, okay, so the test will be inconclusive. Okay, if this fx, fy, the determinant, equal to 0. Okay, yeah. So mostly we're curious, okay, this at here. Okay, let's click here this. Was that okay? So that's basically function of two variables. All right, yeah. So, and this is the essentially it's unconstrained. You know, you have a function, it's unconstrained, and then you're willing to find the mean or max. And the second one here we look at is constrained basically problem, which is actually what our optimal control will deal with. Okay, so constraint is always essentially you have a function you want it to minimize or maximize, but at the same time you also have a constraint. Okay, so which is why we're going to introduce a so-called Lagrange multiplier. Okay, for this type of optimization problem. Okay, so the description would be this. Objective is we wanted to maximize or minimize, okay, a certain function. I'll use function of two variables for illustration at here. Okay, so let's say this is a function we want to minimize or maximize. But this function is also subject to, so we'll just call it ST, okay, subject to a constraint. Let's say this is a constraint at here. Okay, so g of xy equal to c. Okay, yeah, so that's the typical description for this constrained function two variables here. Okay, yeah. So let's say I'll give you a very simple example. I think I talked about this in the 248 too. Let's say if you are designing a fence, okay, a rectangular fence, and this side the length is L, so let's say this side is facing the road, and the other three sides, they are the backyards, right? Okay. So what you know is, okay, you're designing the fence, okay, with an area. You know that you have to be, the area has to be 1200 square meter. Okay, it's pretty big. Yeah. Then you also know that for this side, the facing the road, and you're using a high quality material, $50 per meter. Okay. For the other three sides, okay, we can use a little bit cheaper material, and we can use a $30 per meter material. Okay, yeah. So the question here is, can we come up with an optimized W and an L values such that the cost is minimized? Okay, yeah. So then objective at here is to minimize the cost. And what is the function for the cost then? So the cost C. So cost depends on the length L and the W. So this side of length is $50, so 50 times L. And these three sides are all $30, so 30 times L plus what? 2W times 30, right? Yeah, that's the total cost. And the cost, you put them together, so 80L plus 60W, subject to the constraint, which is the area. So L times W equal to 1200, right? Yeah. So this is basically the optimization problem. That's the constraint problem here, right? Yeah. For this kind of simple ones, you can actually use substitution here. So basically you can say, okay, L equal to, let's say 1200 over W. Then I'm going to substitute, okay, back over here, right? Yeah. So then you can just see that the function C will turn into just a function what? So 80 times 1200 over W plus 60W, and then W on the top there, so 80, 1200, and then 60W squared, right? Yeah. So W is a positive number, so then C, if I minimize, is actually we need to focus only on the numerator, which is a quadratic term. So you can plot it out and find the W. So basically, right, you can use a simple substitution to solve this kind of problem, right? Yeah, so simple ones, okay? Yeah. But we'll use a more generic way here solving it, okay? So let's think about basically this kind of constraint here, okay? So what I'm going to do is I'll go back to this kind of generic description at here, okay? And we'll think about this kind of constraint problem here. Okay, so I'll draw an illustration at here. Okay, so let's say, okay, let's say this is my function, okay, z equal to f of x, y. Okay, yeah. And then we also have this g of x, y equal to c at here. Is that good? Yeah. So constraint means you're not going anywhere but along this curve here, right? That means constraint. So imagine this guy is walking along this curve, and then you will have another guy on the top of the surface, right, which follows this guy here. So at certain so as this guy is walking along this constraint, and this guy will trace a certain curve or trajectory on the surface, right? So somehow, somewhere, you will have a minimum value. So that's basically what we're looking for, right? Or maximum value. Okay? Yeah. So let's make use of a couple of known conditions here. As this is walking along the curve, then I can always use a vector to indicate the direction of walking for this little person, right? It's walking on the curve, then I can use a tangent vector, let's see, okay, unit tangent vector, representing the direction of walking here. That makes sense, right? Yeah. So u hat is a tangent vector to the constrained curve, the path. So as you learned actually, okay, in 248, if u hat is a tangent vector, now if I consider, just look at this guy here. Let's say this is z1 equal to g of x, y, okay, without equal to c, okay, yeah. Or maybe they put this way here. If I set this y equal to c naught, so what do you get? You get the so-called what? Contour, right? You get so-called contour. So this is basically a contour, okay? It's a contour coming from a function z1 equal to g of xy. Is that right? Yeah. U hat is a tangent vector. Then the grading vector del g, okay, grading vector, is always perpendicular to the u hat. So which means the grading vector del g probably pointing this way or the other way, okay? It depends on the function, but it's pointing to the direction of greatest increase, okay? So if you remember, you know, let's say if you have a function of x squared plus y squared, what does that function look like? It's what we call a paraboloid, right? It's a paraboloid. It's a paraboloid, and if you drop this paraboloid to the xy plane, you get a whole bunch of circles, right? That's called contour, right? The contour curve, okay? If you pick a point, then you draw the grading vector. So you draw the grading vector del f. This is f. This is equal to f of x here, okay? Right? So basically, if I look into the xy plane, I see a whole bunch of circles, okay? If I draw a del f, okay, that's the grading vector. It's perpendicular to the tangent vector of the contour curve. And the tangent vector contour curve, that's the u hat, and I'm referring to it here. Okay? That's why I'm putting this. Del g is going to be perpendicular to the u hat. That's number one fact. Okay? Is that okay? Yeah. So number one. So second fact is this. Second fact is the idea of the concept called directional derivative. Okay, directional derivative. So what is the directional derivative? So you are walking along this curve here, right? You're walking along this curve. Let's say at this location you're here, but it will, as I said, this little person will be able to trace out a curve, you know, along this surface here. Okay? That makes sense? Yeah. If you draw a line, basically a tangent to that curve, you get what? You get a slope, right? You got a slope there. So basically at this location, when you're walking in that u hat direction, there is a slope associated with that intersected curve at here. And that slope indicates how fast or how slow or the rate of change for this surface at this location here. That's directional derivative, right? Yeah. So directional derivative is defined as, okay, so df, so let's see here, if you walk along that direction by a very small distance ds, okay, by a very small distance ds, and then you say how much, what's the rate of change of this function f. So basically you see this df over ds. It's basically like a df over dx, right? Derivative. What is df over dx? It's the rate of a change with respect to a small change of dx, right? Yeah. But you're not walking in the x-axis direction. You're walking in the arbitrary direction, which indicated by the ds. Okay. So we need that direction u hat. Indicate the ds is in the direction of u hat, right? That's directional derivative. And directional derivative is related to the gradient and the direction of walking by this formula. Okay, by this formula here. Yeah, those are 248 stuff. Okay. Is that good? Yeah. Okay, so then think about this relate to the mean and max. If this directional derivative represent is the rate of a change of this little person here walking walking along this surface here, then at the mean or at the local mean or local max location, guess what's going to be for the directional derivative? 0, right? So basically at local mean or stationary point, let's see, right? Then this df over ds u hat will be 0. Okay? Yeah. If this is 0, which means del f dot u hat will be 0, right? So that means the del f dot u hat is 0. This is dot product. So what's del f? Del f is a vector. Also, it's a vector in the xy plane. Okay, so here is x naught, y naught, so this location here. So at this location, you have a grading vector for this function, for this surface, right? For this surface here. Okay. Somehow, at local mean or local max, your dot product will be 0 between these two vectors. So what makes the two vector dot product to be 0? The two vector needs to be, they're all in the same plane, perpendicular, right? Yeah. So this is the second fact. At local mean, local max, the del f is perpendicular to u hat. Okay. There's also the first fact. Del g is always perpendicular to u hat. So now you think about it in the plane, in the xy plane. Here's a u hat. Del g is perpendicular to it. And then you also have a del f at local mean, local max. It's also perpendicular to u hat. Okay? So what's the relationship between del f and the del g? Parallel. How do I indicate that it's a parallel? Yeah, sure, but mathematically. Not like this. Mathematically. Two vectors are parallel. What's the parallel means? Okay, what if I don't want to use a dot? I just want an equal sign here. The difference between the two vectors are only a scale difference. Right? Yeah. So this is basically what we're looking for. I'll use a negative here, so just for ease of writing. Okay. This lambda here is what we call the Lagrange multiplier. Okay. Yeah. Okay. So. but ultimately, going through this long-winded description is what I wanted to derive this one here. So at local mean, local max, the grading vector of the function f, okay, is just a scale difference from the grading vector of the constraint function g. Okay, that's basically the idea. Okay. And also, if I go back over here, we can also easily prove, okay, or show that, okay, you see, let's suppose that this location, okay, suppose that this location is a local mean or local max, okay, yeah. So apparently, the del f is a scale difference from del g now. At this location and here, I can also, okay, I can also draw a contour for the function z equal to f of x, y. Okay, so you can also draw a contour basically. I'm not sure what the contour look like. I don't know. Maybe it's a some kind of a circle or curve, right? Yeah. So you can also draw a contour at this location. So that location corresponding to, okay, here, right? Yeah. And then this contour. So at this location, the contour corresponding to this function will be tangent to the constraint, okay, at local mean and local max. Okay. Yeah. So basically, what I can see is at this local mean or max, okay, let's say x naught, y naught, maybe it's a local mean or local max. If I plug in x naught, y naught into the original function, so we get z naught, right? We get z naught. Okay. Then if we let we have a contour saying, okay, so here is f of x, y, okay, equal to the z naught. This is a contour here. This is going to be tangent to g of x, y equal to c. Alright? Yeah. So these two are cotangent. If they're tangent, then you are at this local mean or local max or stationary point. Okay? Yeah. So here I have a better drawing, but anyway, you can take a look at that. Alright, so now let's focus on this guy here, okay? Let's focus on this. Okay. What does del f equal to negative lambda del g give us? Okay, what does this formula give us? Del f is partial f over partial x and partial f over partial y, right? Okay. And del g is partial g over partial x, partial g over partial y. So basically, this equation gives us two equations. Okay? Yeah. First one is partial f of x equal to negative lambda this, right? So it gives us partial f over partial x plus lambda partial g over partial x equal to 0. Partial f over partial y plus lambda partial g over partial y equal to lambda is 0. Okay, so two equations. Okay. Two equations, but you have three unknowns. So you can't solve, right? But remember, we have one more, which is what? The constraint. Okay, the constraint. So now you have three equations, three unknowns, x, y, lambda. Then you will be able to solve, and the solution will be your the solution will be a stationary point basically. Okay, but you have to check if it's a local mean or local max. Okay, yeah. So the focus on the three equations. Now, now what I wanted to do is maybe I can combine basically. Maybe I can combine this these two conditions, basically this condition, okay, and that constraint, these two conditions into one function. So here's what we do. So we define, okay, so we introduce, okay, a function, okay, and this function is this: L x y lambda equal fxy plus lambda g of xy minus c. Okay, we introduce this function, and this function is called a Lagrangian. Okay, so this is called a Lagrange function or Lagrangian. Okay. And I can state that the original constraint problem is equivalent, okay, basically to an unconstrained problem, optimization problem for the L now. So originally you have a constraint optimization problem, finding local mean and local max subject to the constraint, right? So now I can see that I'm trying to find the local mean and local max for the L, and it turned out to be the same solution as the constrained one. Why is that? So if you look at this one here, okay, so this guy here is called the Lagrange multiplier. Okay, if I look at this one here, so how can I, what's the first step? The first step is first derivative test, right? First derivative test. Now first derivative test means you calculate del L, right? The gradient vector del L equal to 0. Okay, equal to 0. So del L equal to 0, and this is the necessary condition. Yeah, this is a necessary condition for the optimization, right? For the optimality. Okay, for the optimality here. Okay. So what does del L give us? Let's see. Del L meaning partial L over partial x equal to 0. Partial L over partial y equal to 0, and partial L over partial lambda equal to 0, right? Yeah, that's del L. So you look at this one here. What does partial L over partial x give us? Function of multivariables. Partial f over partial x plus, expand that, lambda partial g over partial f. Right? Look at this one here. That's this, right? Okay, that's this. The second one here, partial f over partial y, and lambda partial g over partial y. Okay, and the last one, what's partial L over partial lambda? There's no lambda here, there's only lambda here, so you end up with this, right? You end up with this guy here. And what does this give us? That's the constraint, right? It's constraint here. So basically this Lagrangian at here, right? The function, Lagrange function, okay, finding a local mean or local max, finding the optimality of this function is equivalent to that original constraint problem. Okay, yeah. So in the second word, basically we're turning a constraint problem into a what? An unconstrained problem. Okay, yeah. So that's the idea. Okay. In the next lecture, we are talking about LQR, optimal control problem, and this is what we're going to do. Okay, so we're going to introduce the Lagrange multiplier. Okay, and we'll have our constraint. We will have our cost function. Okay, so typically this guy here will be called FLCS here. They'll be called cost function. Okay, and this will be the constraint. Okay, yeah. So let me give you an example right here. Okay. and let's take a quick look at this application of this, and then we'll look at a little bit other things. Okay. So let's say I have a function that I wanted to minimize or maximize, okay, which is this guy here. Okay. Yeah. And the constraint is xy equal to 3. Okay, that's a constraint. So for this function, as I just draw, this is a paraboloid function. Okay, paraboloid function. So this function definitely has a local mean. Okay, see, right? Yeah. This is actually what we call, it's a convex. Okay, it's a convex function. So when you have this kind of convex, it's basically there's a mean there. Okay. Yeah. So what is xy equal to 3 then? This is xy. What is xy? This is a constraint, right? If there's no constraint, where's the mean? It's right here, right? It's a 0. X equal to y equal to 0. But your constraint is x equal to your constraint basically it's this, right? Yeah. That's your constraint. So basically your constraint is you have a curve, okay, like this, and there's another portion on the other side, right? Okay, that's your constraint. And you can think of walking is along this curve here. So when you're walking along this curve, then there's going to be a curve traced out on this surface, right? On the surface here. So that curve, I don't know what it looks like, but I'll show you, use a better one there. So it's going to be a curve like this, okay? Yeah. It's it's actually not a plane one. It's there is a certain, basically it goes right. Yeah, it's not in the same plane. Okay. Yeah. So there will be a minimum value which corresponding to somewhere like this. That makes sense? Yeah. Okay. Yeah. So that's what we're trying to find. Okay. So here's what we can do. We can use our Lagrangian at here. So form a Lagrangian using the constraint and the cost function. Okay, so we're going to form our Lagrangian like that. Okay, and then we're going to calculate the gradient of this and set it equal to 0. So we get three equations. Okay, first one is this. Second one is this. Last one is the constraint. Okay? Yeah. So good? Yeah. So three equations, three unknowns. You should be able to solve, but they're not linear. So they're non-linear a lot of time. So solving this kind of thing sometimes it needs a little bit, examinations there. Okay? Yeah. But here's one way of solving it. Basically, from the first two equations, and I can put it into a matrix. So 2 lambda lambda 2 and times xy equal to 0. Okay. Yeah. Then to make this equal to 0, right? To make x equal to 0, the solution is either x equal to y equal to 0. Okay? But that's not possible. Because why? Because this is not on the constraint, right? It's not on the curve. So this is not good, right? And then to make this 0, the other condition is what? It's the determinant of this matrix to be 0, so that you can't take the inverse anymore, right? Yeah. Okay? So basically, all the determinant of this matrix to be 0. And that gives us lambda equal to positive and negative 2. Okay? Yeah. So then what you next to do is you say for lambda equal to 2, okay, and then substitute it back, and then you have now you have a 2x plus 2y equal to 0 and xy equal to 3. Okay, yeah. So you solve these two now, right? It's pretty easy. Okay, yeah. But when you look at this one, you'll try to solve. There's no real solution in here actually. Okay, so this guy here is no real solution. So we're gonna just discard it. Okay. Now we're already in a 3D real domain here. So then lambda equal to -2. We have this one here, and now this one here has a real solution. So √3, √3, and -√3, -√3. So that makes perfect sense, right? If I look at my drawing here, I mean, apparently there's a mean at here, right? That's possibly √3, √3. And on the other side of the curve, that's probably -√3, -√3. Okay? Yeah. That's it. That's basically the local mean location. Then you can calculate. So what is the actual mean value, right? So actual mean value is basically √3 squared plus √3 squared, or the other one. It gave us a 6. Okay? Yeah. Was that okay? Yeah. So here's a maple animation at here. Okay. So this is the f function equal to x squared plus y squared. And then the little dot at the bottom there, okay, is going to walk along the constraint. Okay, and the dot on the surface will follow the dot in the xy plane. Okay, so you can see that, and then this circle there, okay, is the contour. Okay, is the contour at the local mean there. Okay, so you can see apparently what the constraint and the contour for the surface at local mean, they are tangent, right? They're tangent. Okay, so you can take a look at second look in here. Okay, yeah. Oh, I'm sorry. This is not xy. This is not xy equal to 3, isn't it? Right? This is a straight line. So where's my xy equal to 3? It's probably here. Let's save this guy here. Yeah. So this is xy equal to 3 constraint. Okay. Yeah. You see this curve here, right? That's xy equal to 3. Okay. So actually, oops, it's too big. So actually, you can try to look at the two vectors, the green one and the blue one and the red one. Okay, the blue one, I don't remember which one is which now. Anyway, one is the grading vector for the xy function, and the other is the grading vector for the x squared plus y squared. Okay, so you see that at local mean location, if I move, so right here, see what happens? The two vector, they become parallel, right? That's basically del f, del g is a scale difference. Okay, and that location, right, corresponding to that top one there, that's the local mean, right? That's the local mean there. Okay, yeah. So as you can see, that curve is not in the plane. You know, it's actually sort of inclined there. Okay, but you have a local mean there. Okay, yeah. All right. Anyway, bottom line is, right, if you have a constraint problem, and you can basically use that Lagrangian, okay, to put things together. Okay, yeah. Okay, so And last point, and I want to make is, okay, and also often in time, what you have is a question like this. So there's a different perspective of the question here. Let's see if I'm going to let this q of xu, okay, be the so-called cost function, or sometimes we also call it performance index, so PI. Okay, yeah. And maybe u is a control input. Okay, it's a control input. Yeah. So the idea is we wanted to basically, let's say, a lot of time, maybe this is actually represent is a energy. Maybe it's x squared plus u squared. Okay, so x maybe it's a state and u is the input, you know, and then the 1/2 x squared plus 1/2 u squared basically represents the concept of energy, and we want to minimize the energy consumption. Let's see, right? Yeah. And then subject to constraint. Let's say the constraint is, and this guy here. Okay, yeah. So this is not necessarily the best constraint. Actually, later when we have a dynamic system, so this dynamic system here is probably x dot equal to this. Okay, that's the dynamic system. Okay, yeah. So then, given this kind of system now, then we can basically form a Lagrangian okay, like this, and then we can try to get the del gradient set equal to 0. Try to get the stationary point or mean point, local mean or local max, right? Yeah. So the u at here. So this is basically more of a concept. Control input, more of a concept now related to control system. Okay, not complete yet, right? Okay, one step closer. Okay, so but the other one is, okay, what we might have is not just one constraint. So we may have a multiple constraint. Okay, yeah. So if you have a system, the order other than 1, maybe you have a second order system. You have a state space equation. If you have a state space equation and represent a system order 2 or 3, then you would have how many state to equation now? You would have 2 or 3 state equation now, right? Yeah. And those are all constrained basically, right? Yeah. It's constrained to the system. So if we have a multiple constraint, okay, then what we can do is, right, here is first constraint, let's see. The second constraint. Okay, let's keep going. Yeah, and maybe there are n number of constraints. Right, n number of constraints here. Okay. Then when you form the Lagrangian, so you can form the Lagrangian like this: L, X, U, lambda 1, lambda 2, and lambda n. Okay, put all of them together. And this guy will be equal to Q XU plus, let's see, this is all still our performance index, plus lambda 1 G1 XU minus C1 plus until lambda n Gn XU minus Cn. Okay? Yeah. So same idea, right? You just write a few more terms. Put them into a matrix format. Okay, put them in matrix format. So what we can do is, let's see, I define a column vector lambda 1 to lambda n, and I define a constraint function as then this Lagrangian L could be just x u lambda, right, equal to q x u plus lambda transpose time g vector. All right? Yeah. Okay. To make it even more complicated, your x could also be a vector, right? So you can have multiple states. This is actually what we're going to deal with, okay, in the next lecture. So from simple to more generic complicated case, but you should also bear in mind is you don't be scared about the complication. You should bear in mind the fundamental didn't change, right? The fundamental doesn't change, still there. It's the same idea as a single variable, same idea as a function with two variables, okay? Yeah. So that's basically what we're going to deal with in the next lecture. Okay. However, okay, I just want to do a quick review, a very simple review here. When this becomes a vector instead of just a scalar at here, where did that red dot go? Yeah. So when you're dealing, okay, with just a vector instead of scalar, the calculus or the derivative, okay, will be slightly different now. So because, for example, you know, if you see what's the partial L over partial x, right? So instead of saying just partial x1 or partial is a scalar for x there, so this is going to be a vector, right? Or let's say, what about the partial L over partial lambda, right? Yeah. So this is basically what I'm saying. The derivative was the format was slightly different, and we're dealing with so-called matrix calculus. Okay. Yeah. Again, remember what I said. The fundamental didn't change. Okay. It's still calculus. It's just because the vector matrix now, so that's why it's called matrix calculus. Okay. Yeah. Very simple. Let's see. Give you here just a quick one. We're probably not going to do too much of it here. We can do a little bit more in the next lecture. Let's see if I have. Let's see, for example, if I have a function qx equal to xax here. Okay. This is mostly what we're going to do. This is called a quadratic form, right? Remember I said this is a quadratic form. Okay. Yeah. If I'm going to do this, it must say is. What is a partial q over partial x, like this? Okay, what's a partial q over partial x? Okay. Yeah. So, bearing in mind is x is a n by 1 vector, real vector, and a is a n by n, okay, matrix. Okay, yeah, square matrix. So then this piece, okay, if you look at this piece right here, the q is actually a scalar. Okay, this is basically a scalar here. You know what I'm saying? Yeah, what's common with q is a scalar function. But it's a function, so q is a function what? It's a function of x1, x2 to xn. Okay? Yeah. Then when we write partial q over partial x, okay, this is actually just the first Jacobian there. So this we're going to see. This is going to give me a column vector here. Okay, it's going to be giving me a column vector, and that equal to A transpose x times ax. Okay, A transpose x times ax. Okay. That's matrix. Okay. Now, if A is symmetric Okay, if A is symmetric, then the partial Q over partial X, AT is the same as A, so 2AX. Was that good? So we're actually going to make use of quite a bit of these results here, okay? Yeah, in terms of our derivative. Because ultimately, you see, when you have vector, when you have this, what do we do? Next first step is the first derivative test, right? So we're going to have to need partial L over X or partial L over lambda vector. Okay? So there's a lot of things in here, but I'm going to talk a little bit details in the next lecture. Okay? Any questions? Okay? Yeah.